Starting from this action here, I want to rewrite this part of the action where we have these four elements of the field. In particular, phi hat is the discretized Fourier transform of the field phi. So we have this hat to remind ourselves that there is a transform. Anyway, each of these fields, so for example, phi sub n hat, can be written as its mod, so its modulus or its magnitude, mod phi n times a phase. So the phase, we can write it as e to the plus or minus I. So let's write it as I phi sub n. So this is the phase associated with this complex number. By the way, this is just a complex number which depends on the subscript n, and this is the mode of the complex number itself. So when we have a lot of these terms, remember that these integers n1, n2, n3, and 4 can go from minus infinity to plus infinity, so they are integers, and for the sake of convenience, we are assuming that phi hat sub 0 will be 0. So this will simply mean that the average of the field phi will be 0. So in particular, phi sub j, summation over j of phi sub j from, in general, from minus infinity to plus infinity. So you just sum over all the possible subscripts. So you sum over all the possible fields, phi 1, phi 2, phi 3, phi 3, phi infinity, or if you start at minus infinity, you can think that the summation starts at minus infinity, but that's not really the point. You sum over all these fields, phi 1, phi 2, phi infinity if you want, and we are saying that this is 0. So this is proportional to the average of the field, and we are assuming that this average is 0. So this is the lowest mode of the field. The lowest mode is the lowest energy, so that's the average or the mean value of the field. That's not going to take anything away from the physics that we are analyzing. So this is without any loss of generality. Remember that phi sub minus n is equal to the mode of phi sub minus n, but the mode of phi sub minus n is equal to the mode of phi sub n. And then the phase of phi sub minus n is equal to minus I phi sub n. So that's why we can say that for a real field, phi sub j, for example, we go to the Fourier domain and its Fourier transform, for example, the phi hat sub n, and if we take the complex conjugate of this, so phi sub n hat star is equal to phi sub minus n hat, or phi hat sub minus n. So this is what you get. And assuming that these phases here are randomly distributed, this phi sub n, in particular, let's consider them to be part of a uniform distribution. So they are uniformly distributed, and the result will only depend on the amplitudes if you think about it. So if you sum over all the possible values, these phases will cancel each other, and this is also something that's reminiscent of the path integral, where all these phases will annihilate each other, and only the part that's close to the classical trajectory will give any kind of significant contribution, whereas the part that's very far away from the classical trajectory will give you zero contribution. That's the concept, that's the idea, and let me tell you more about it. And let me also tell you that you can also have some more insights. You can gain some more insights if you check, for example, the courses on the central limit theorem derived from stochastic processes, or the math of random signals, fatigue damage, and vibration tests, if you are interested. But you don't have to check them out. If that's just if you are interested in it. Anyway, let's start from here. And let me tell you that Since we don't have anything that's dependent upon the phases, so at the end of the day, when we sum all the contributions, we will not get a result that's dependent on the phases. And this means that from this condition here, from this summation, we will have to get terms of the following form. So we will have to sum over such terms, mod phi sub n squared times mod phi sub k squared for some values of k and n. And for example, phi sub n will be phi hat sub n times phi hat sub minus n. This is exactly the mode of phi sub n squared, and this can also be interpreted as phi hat sub k times phi hat sub minus k. All the other terms, they will be dependent on the phases, and when we sum over a large number of them, it makes sense to think that they will give a zero contribution. Now, if we think about this, remember that we start from the indices n1, n2, n3, and n4, and they have to satisfy the relation n1 plus n2 plus n3 plus n4 equal to 0. And they should, all these indices should produce only terms of this kind, or if you want, this kind here. Now, this is possible if, now think about it, this is possible if, for example, we have n1 plus n2 equal to 0, which means that since these two conditions should be satisfied together, n3 plus n4 should also be equal to 0. Or if n1 plus n3 is equal to 0, which means that n2 plus n4 is also equal to 0, or we also have a third condition, n1 plus n4 equal to 0, which means implicitly that n2 plus n3 should be 0. Now, these conditions, due to the symmetry of the indices, are equivalent to one single of these conditions repeated 3 times, right? So basically, from this summation, you can understand that we will get something like this, proportional to 3 times summation over one index that we can call n1 mod phi hat sub n1 squared, and then we sum also on another index n2, and we have phi hat n2 squared. But we have to be a little bit more careful because there are some corrections to be made to this kind of result that we get. Because if you think about it, so this is quite subtle, but let me explain it. If you think about it, that when we consider, for example, the following 4 indices, so n1 equal to, let's say, 1, n2 equal to minus 1, n3 equal to minus 1, and n4 equal to 1. So this is an example, but it will let you understand. We have the absolute value of the indices that are the same, so they're exactly equal. We are thinking about the absolute values, so not the specific values, but the absolute values, they are just the same because the absolute value of minus 1 is equal to the absolute value of 1, right, which is 1. We have some overcounting in this condition here when we consider the same absolute values of the 4 indices. And let me expand on this. Why? So this is an example. In particular, we see easily that n1 plus n2 plus n3 plus n4 is equal to 0. So this is satisfied. But let me also tell you that n1, here this index n1, can be paired with n2. So we have n1 plus n2 equal to 0, and you can see that n3 plus n4 is equal to 0. So we see that this is satisfied, but you can see that simultaneously we also have n1 plus n3 equal to 0, and also n2 plus n4 equal to 0. So you can see that when the absolute values of the 4 indices are exactly the same, we can see that there is some overlap between these two conditions here, right? So you are counting twice the same thing because the indices are just fixed. They are 1, minus 1, and plus 1. So you can see that this should be counted only once. But if you think about it, when we split this condition here into these three parts, which are those that give the significant contribution, the non-zero contribution, you can see that there is some overlap when the absolute value of the indices are the same. So we are counting this twice, and we have to avoid that. So this basically means that the result of the summation will not be exactly equal to this, but we have some correction to make. In particular, these three will remain there. And we have this summation, but we have to subtract the summation over n of mod phi hat sub n to the fourth, like this. So when we subtract this, you can see that here we are considering the indices of the same absolute value. So when you see the mod of phi sub n to the fourth, it means, for example, that when n is equal to 1, so we have phi hat sub 1 to the fourth, this is equal to mod phi hat sub 1 times mod phi hat sub minus 1, or in particular, you can also write it without the mod, phi hat sub 1, phi hat sub minus 1, phi hat sub 1, phi hat sub minus 1. For example, this is exactly, or it is similar to this condition here, where n1 is this value, then we have n2, n3, for example, I've written it here, so this is n3, and then f4, n4 is equal to 1. So you can see that I'm subtracting these terms in such a way that we are counting such terms only once instead of twice. So that's the point, and this is a subtlety that I wanted to address. And in principle, when you have a very large number of these terms, this term here will be negligible with respect to this. But it is just a subtlety that I wanted to highlight because indeed this is something to be considered, to be very general, to be more precise. And this summation can also be written as summation over just one index n mod phi hat sub n squared, and then we square it, right? Because this single summation that I've written like this is actually a summation over n1, and then I have also a summation over n2. So when you square this this sum, you have summation over n1 mod phi hat sub n1 squared, and then you also have a summation over n2 mod phi hat sub n2 squared, and this is also equal to summation over n1 summation over n2 mod phi hat sub n1 squared mod phi hat sub n2 squared. And for the sake of convenience, and in order to lighten notation, this can also be written as just with just one symbol, and then with let's say under the symbol we write n1 comma n2 to denote the fact that we have to sum over n1 and also over n2, and these two indices are independent of each other, so we are just summing over all the possible values. And therefore what we have found is that, so let me rewrite it more clearly, we have found that this summation here, summation over of such terms, phi hat and 1, phi hat and 2, phi hat and 3, phi hat and 4, we are summing over n1 and 2 and 3 and 4 in such a way that this relation is satisfied, n1 plus n2 plus n3 plus m4 is equal to 0. And we found that this can be written as 3, and this 3 is related to the fact that these three conditions, 1, 2, 3, they give exactly the same result. So there is symmetry in the indices, and you have summation over n, and then you have mod phi sub n squared, this is squared, minus summation over n mod phi hat sub n to the fourth. So we will keep this in mind because we can replace this term in the action with the result that we just found. And then once we have that, we can calculate the propagator of the theory. In particular, we will have to make some approximations because we have to use perturbation theory. So we will have to make an expansion to be able to calculate the corrections to the classical propagator. We will see that, and then we will see exactly that we will find some Feynman rules. We'll get some Feynman rules that we should expect from just applying the rules. In this case, what I want to do is to derive the rules starting from the action. We have discretized the action in this way, and I will give the details in the subsequent lectures.